Can you hear me now? Or do I need to speak? No? Higher? I guess maybe I can hold it. Is it better now? Can you hear me in the back? No? Okay. Okay, maybe I can just hold it in my hand. I think that would be easier. Let me try to put it somewhere, maybe central. This is not very high. What about now? Is it better? Okay, I will try also to speak a bit louder than I generally speak, and hopefully if you really cannot hear me, just make signs and I will try to be a bit louder. So in these last two lectures of the school, I'm going to introduce some new capabilities that are implemented in EPW, and these capabilities allow to look at superconducting properties with anisotropic resolution. Since I suspect that not everybody has worked with superconductivity, I will start the presentation with an overview of basically what is superconductivity and what is the field of superconductivity at this point. Then I will overview the BCS theory of superconductivity and briefly mention the McMillan-Allendice formula for critical temperature that you have already seen in one of the tutorials. And the central part of the talk will be the Migdal-Eliashberg approximation and the Nambu-Gorkov's formalism that put together allow to derive what is called the Migdal-Eliashberg equation. And finally, I will just mention briefly another method to investigate superconductors from first principle, which is density functional theory for superconductors. So superconductivity is basically a quantum mechanical phenomena occurring in certain materials below a characteristic critical temperature. And at the macroscopic scale, there are two very intriguing manifestations that one can observe. So one of them is this zero resistivity. So basically, below the critical temperature, the electric current can flow without any resistance. And this was discovered in 1911 by Ons. And then the second manifestation is, for example, the perfect diamagnetism. So basically, a magnetic field is expelled from a superconducting state. And this was discovered in 1933 by Meissner and Oschenfeld. So since basically superconductors can carry very high current densities and can generate very high magnetic fields, they can find numerous applications. And currently, the largest market for superconductors are MRI machines, but for example, the Large Hadron Collider in Europe would have not been possible without using superconducting magnets. And also for over a decade now, we have magnetic levitating trains. The reason why superconductors are still not widely used is that because they operate at very low temperature. So ideally, we would like to have superconductors that can function at room temperature. Working at nitrogen temperature, it would still be fine since nitrogen is cheap and abundant. But unfortunately, as I said, the widely used commercial superconductor, they operate at helium temperature. And this is not sustainable in the long run because helium is scarce and also expensive. Yeah? So we are going to run out of helium at some point. So traditionally, the progress in superconductivity is shown by a plot like this of critical temperature versus time. So as you can see here, until 80s, the highest temperature, critical temperature that was known was around 20 Kelvin. And I should mention that all these superconductors are what we call conventional superconductors. So the mechanism is due to the, it's phonon mediated, so it's due to the interaction between electrons and phonons, the lattice vibrations. Then in 1986, that was the first major breakthrough in superconductivity research when it was discovered that superconductivity in oxides was discovered. So very quickly, the TC in the oxides exceeded basically 70 Kelvin, and it was hoped that this is going to bring a lot of changes in the application of superconductivity research. Unfortunately, these oxides are ceramic materials, and they are very hard to be manufactured into wires. I'm not going to go over all this plot, but I am just kind of mention main breakthrough in this area. So the next, I should have also mentioned that these oxides have they are called unconventional superconductors, and the mechanism of superconductivity in these materials is not phonon mediated. Yeah, it's not really known, but it's known that it's not phonon mediated. The next breakthrough in the area was in 2001 when a well-known compound, in this case magnesium diboride, so it was a compound that was in a lot of on the shelf of a lot of experimentalists, was found to be to have a TC of 39 Kelvin, and this is a phonon-mediated superconductor. Yeah, so this has been had a phonon a major improvement in compared to the superconductors that were known in the 80s. The next significant milestone was the discovery in, I believe, 2006 of iron-based superconductors. These are also unconventional, but still unlike the oxides. And finally, just recently, superconductivity have been discovered in sulfur hydride under pressure, and in fact compressed sulfur hydride, and this is also a phonon-mediated superconductor. Yeah, so this is just a general overview of where the superconductivity research is standing at this point. I guess I should move also on this side. Now, as I said, the next step we are going to talk about the BCS theory of superconductivity, and this is the, I think here you cannot hear, no? And this is the first microscopic theory of superconductivity. So the BCS relies, or the main assumption in the BCS theory is that there is some kind of attraction between electrons that can overcome the Coulomb interaction. And to see this very easily, we can look at two electrons in a system. So, for example, if we have a crystal and we have an electron moving in one direction, then the electron is going to create a deformation of the lattice with a net accumulation of a positive charge. As a result of this lattice deformation, another electron moving in the opposite direction will be attracted in this region of this highest positive charge. As a result, the two electrons become correlated and they form what is called a Cooper pair. Yeah? So I should mention that in the BCS theory, this pairing, like the type of pairing, the potential that creates this pairing is not really, it can be general, but in the case of conventional superconductor, the pairing is due to the interaction between electrons and this phonon vibration. Yeah, so this picture that I'm showing here is when the pairing is due to the vibration, the coupling between electrons and phonons. And so as I said that the two electrons become correlated, And there are many such pairs in a material. So since these electron pairs overlap over each other, they form what is called a highly collective condensate. So at very low temperature, this electron, the electron can stay paired, and they can resist any kicks from the lattice. So in other words, the electrons can carry current without an energy loss. So yes, we will have this, the resistivity in the superconductor is going to be 0. So we can see also this pair formation. We can also present it in a simple, I think this has stopped working. Oh, okay, finally. So we can also look at the mechanism, at the electron pair formation in this simple diagrammatic representation. So in this case, let's say that we have an electron in a state K that emits a photon, and as a result of this emission, it moves to a new state with momentum K prime. The photon will then be absorbed by another electron with momentum minus K, and this electron will move in a new state with momentum minus K prime. So effectively, what happens is that two electrons scattered on each other by exchanging a phonon. And since for this basically scattering to occur, we need to have the state with momentum K prime and minus K prime need to be unoccupied. Yeah? And this can only happen if these states are in the vicinity of the Fermi energy. So basically, the electrons that form the Cooper pairs are within a layer, or in other words, these active electrons are only in a thin shell in the vicinity of the Fermi surface, and the thickness of this shell is determined by the characteristic phonon frequency of the material. So this is basically of the order of the largest phonon frequency in your system. So it's only of the order of milli-electron volts. Yeah? For example, magnesium diboride, the highest phonon frequency is around 200 milli-electron volts, just to get a rough idea of what energy scale we are talking about. So I should pause now and say that basically this collective state that is formed is a key thing to bring in superconductivity. Yeah? So if we don't have this Cooper pairs formation, we are not going to have a superconducting state in a metal. And finally, also a general picture. How do you do it? Okay. We can compare the density of states in a normal metal and the density of states in a superconductor. Yeah. So in a normal metal, we have that the electronic bands below the Fermi level, all electronic bands below the Fermi level, are fully filled, while all energy bands or energy states above the Fermi level are fully empty. On the other hand, in the ground state of in the BCS ground state, we have Cooper pairs. So in this case, while single electrons are fermions and they should obey Pauli exclusion principle, electrons in Cooper pairs are boson-like particles. So in other words, they can condensate and they can occupy the same energy level. Yeah? So as a result, what happens is that a gap opens in the single particle excitation spectrum of a superconductor. Yeah? And this gap is this 2 delta, and it depends on temperature. So we can see that we will see the behavior in the next plot. And basically, this 2 delta is the binding energy, the energy required to break a Cooper pair. Yeah, so now again, if you want somehow to compare to a semiconductor, here this energy gap is of the order of milli-electron volts. Yeah, while in semiconductors you talk about band gaps which are order of fraction of electron volts. So it's again a different energy scale. And you should also notice that here there is a peak in the density of states. So this is because we are now moving these electrons from the states that were initially this part, occupy this part of the valence band that right now is empty. Okay, so we can move a bit further, and now it will start becoming more formal with the theory and introducing some equation. But basically, this superconducting gap can be solved, sorry, can be obtained if one solves what is called the BCS gap equation. So in this formula, you will see that there are a number of indices, but it's quite simple. So
you're simply too far away from the computer.
I see. Maybe here even the sound is better.
No, it's for the...
Sorry. Get a sip of water. So in this formula, we can try to understand what each term represents. So delta, sorry, is the superconducting gap, and V is the pairing potential. So this is the pairing potential that we said I mentioned earlier when I was describing that picture, and then E and K is the quasi-particle excitation, which is expressed in terms of energy eigenvalues, single particle energy eigenvalues, and the superconducting gap. And then you can see that we need this has basically an anisotropic form. Yeah? So you can solve it for any index band n and momentum k, and then here you need to sum over all phonons. Yeah? So it will be the Q point. So if you were to solve this equation, which I'm not going to go through the math this time, you will get a function like this. Yeah, this is the behavior of delta as a function of temperature, and what you can see is that at t equal to 0, the gap has a maximum, and at t equal to the critical temperature, the gap becomes 0, vanishes. Yeah, so once you pass, your temperature goes beyond the critical temperature, you are in a normal state. So if you were to look at this previous picture, you will end up again with a metallic system. Yeah, so your band gap is will close. So just to summarize briefly the BCS theory, this theory describes in detail the phenomenology of superconductivity. However, you should still keep in mind that this is a descriptive theory. So in other words, it's materials independent. And in fact, it predicts this relationship between the superconducting gap at 0 Kelvin and the critical temperature. And most importantly, the method, the model, the theory does not account for the retardation of the electron-phonon interaction. So what does that mean? If you remember the previous picture, sorry for going back and forth. If you remember this picture, I said that when an electron moves to the crystal, the ions are going to also move, and they are going to perform a deformation. So in other words, the time it takes for ions to move to displace from their equilibrium position to their maximum displacement it's inverse proportional to the characteristic phonon frequency. So in other words, smaller the characteristic phonon frequency of the material, longer the time that it takes for an ion to reach this displacement. Yeah, so longer the retardation, and this retardation effect is missing in the BCS model. Yeah, so it's considered that the electron-phonon interaction is basically instantaneous. Questions this far, so far? Yes.
So apparently the formula superconducting gas depends on direction.
So you can then average over the Fermi surface, yeah, and you will get a simple gap like this.
Can I?
Yeah, in principle, you can solve it like this as well, yes.
So just by looking at this, so can I say that the energy required to break the superconducting state at different transport directions is different?
You can see an anisotropy in the superconducting gap. So we'll see that later also in the Migdal-Eliashberg formalism, and I'm going to show some results that will show you how the gap looks when you calculate with all these factors with the anisotropy. This will become more clear when I will show a few examples.
And one more question. So by looking at this, is it possible that superconducting gap closes in one direction but still open in the other?
It depends on the Fermi surface, yeah. So depends on the form of your Fermi surface.
So in principle, it's possible.
Yes. So right now, let's see how TC is in fact calculated in practice nowadays beyond the BCS model. And as I said, I will briefly go over the McMillan-Allendine's formula that you have already seen in, I think, on Tuesday. So in this approach, we basically can evaluate, or we can predict the critical temperature. I think if I stay on this side, somehow I can realize that I speak louder. I think it's the microphone is on this side. Sorry, I will have to point to this slide. So in order to predict the superconducting temperature, we can do it once we know the electron-phonon coupling strength, yeah? And this, we can see, we saw that we can calculate ab initio. And the other parameter that enters in this formula is what we call the semi-empirical Coulomb pseudopotential. And this omega log is just an average phonon frequency. So in fact, the majority of ab initio calculation that exists in the literature rely on this formula. And the reason is that it's quite, all you need is basically a value for lambda. So it's easy to calculate, and it's been around for many years in Quantum-Espresso, and I believe probably since you can estimate lambda, this can be done also with ab init. And this formula works reasonably well for isotropic superconductors. And the reason why it works for isotropic superconductors is because it's been determined, or it's been derived based on the isotropic parametrization from results for isotropic Migdal-Eliashberg equations. However, you should keep in mind that in order to get converged value for lambda, and as hopefully you have realized at this school, is that you require very dense K and Q meshes. Another thing where this critical temperature, this formula fails, is that the critical temperature that we predict for anisotropic or multi-gap superconductors will be wrong. Yeah, so it doesn't capture any anisotropy. Also, you only predict the TC. You don't really have any information about the superconducting gap. And then it also approximates the Coulomb interaction to a semi-empirical parameter. Yeah? So this is usually chosen between 0.1 and 0.2 for most materials. Now, we can move on and finally start talking about the Migdal-Eliashberg theory. And this theory was developed in 1960 by Eliashberg that generalized basically the BCS theory of superconductivity by introducing the time-dependent electron-phonon interaction that was developed by Migdal for the normal state. So this formula for the pairing self-energy, which is the central part where we start with in the Migdal-Eliashberg theory, should already be familiar, since this has been shown in lecture, Feliciano's lecture on Wednesday. Yeah? So this is nothing else but the Fan-Migdal self-energy, where the vertex, gamma vertex, was neglected. Yeah? So this is the D is the Dress-Phonon propagator. G are the electron-phonon matrix elements that we can calculate, and this capital G, this operator, this is the interacting Green's function. While this term here describes the electron-electron interaction, and basically it can be in principle calculated, is the GW self-energy, and can be obtained from GW calculation. Yeah. And the fact that we are neglecting, we are only keeping the first order terms in the electron-phonon self-energy, a finite diagram for electron self-energy in superconductivity is called the Migdal's theorem. It's referred to as the Migdal's theorem, and is based on the observation that neglected terms are of the order of the square root of the electron mass to the ion mass, and this can be shown that is proportional to the characteristic phonon frequency. This will be the Debye frequency divided by the Fermi energy. So we talk about a ratio of MeV to electron volts. Yeah. Now you need to keep in mind if if the phonon energy is of the order of the Fermi energy, this approximation may break down because this is based on the adiabatic approximation. As far as I know, there are no studies that have investigated at which point the Migdal's theorem is, breaks down. So now we can, the next slides, I don't remember, 4 or 5 slides are quite intense with math. So if you don't get them, please don't get desperate. If you later on you can go through them and you can work out, and you are going to realize that it's the formalism is not that complicated. Yeah. So this is the again the pairing self-energy for the electron, and what we can do as the first step, we can replace the phonon propagator. Or we can rewrite the phonon propagator in its spectral representation. Yeah, and that's already again, if you go yesterday's lecture by Feliciano, he has already given this expression for the Dress phonon propagator, if I remember correctly. And then another trick that we can do here, we can now introduce a new quantities that that couples G with the Dress phonon propagator, and this we call the anisotropic electron-phonon coupling strength. Yeah, so this we can see that it has the electron-phonon matrix elements, and compared, we can see later on that this is basically the same electron-phonon coupling strength that we have seen before, only that now we keep the full anisotropy in the expression. Yeah, so it depends on the initial state nk and the final state mk plus q. So if these two equations are plugged in the, if we now use lambda in the self-energy expression, we can rewrite it in a bit more compact form, where lambda can be easily calculated once we know the electron-phonon matrix elements. And as I said, the Coulomb interaction can be in principle calculated through a GW approach. So what we are left right now, in order to estimate the pairing self-energy, we need to find this non-interacting green function. Yeah. So in the Migdal or in the superconductivity state, this is, I would say, it's formally done, or it's more easily done if we use what is called the Nambu-Gorkov formalism. So within this formalism, we can describe the propagation of the electron quasi-particle and of superconducting Cooper pairs using a generalized Green function. Yeah, so this is the generalized Green function, and again, this looks quite familiar, or you have to what we've seen on Wednesday. Yeah, so this tau, it's an imaginary time. This t tau is the VIX time ordering operator, and the only difference while on Wednesday this was just a single operator, now is a two-component field operator. So it has basically two components. One component destroys an electron at a state nk and spin up, and the other electrons, the other operator creates an electron at a state n minus k and spin down. I forgot to mention, but in the BCS model, it can also be shown that the Cooper pairs are formed not only between electrons with opposite momentum, but also with electrons with opposite spins. Yeah, so this will become basically, this picture can be reduced to the BCS model. So now, if we plug in this field operator in this expression, you can see that we have a column vector multiplied by a line vector. Yeah, so this is just the complex conjugate. So what you are going to get is a 2x2 matrix element. Yeah, and now let's pause for a moment and let's try to understand the elements of this matrix. So now, if we look on the diagonal, what you can see is that you create and destroy, or here you destroy and create electrons, but what is important, they are on the same state. Yeah, so this should tell you that we are now talking about normal state Green functions, and this basically, they describe the single particle electronic excitation that we will have in a normal metal. Now, if you look at the off-diagonal elements, you can see here that you either destroy or you either create particles, but these are in different states. Yeah, so one state is with momentum k, the other is with momentum minus k, and then these are spin up and spin down. And as I said, this is basically what we have when we form a Cooper pair. So this off-diagonal elements are called anomalous Green functions and describe Cooper pairs amplitude. So basically, if these off-diagonal elements are zero, as I said, you will just have the behavior of a normal metal, and when these elements, and these elements are basically non-zero only in the superconducting state. Now, since this operator, this generalized operator in the imaginary time is periodic in tau, it can be expanded in a Fourier series. And mathematically, this is convenient because now we need to calculate this matrix elements, what we call on the Matsubara frequency axis. Yeah? So these are just discrete values. They are integer of J, and they depend on temperature. Yeah? So this is how temperature effects are introduced through through Green's function. And we can see here that larger the temperature, farther apart this imaginary frequency points will be on are on the imaginary frequency axis. And in fact, this can cause issues with convergence when you start doing numerical calculations, when you have fewer and fewer points in this sum, because at some point you need to truncate this sum, and fewer points you have, harder will be for the algorithm to converge. So what we are left with right now, as I said, we now need to estimate to find this generalized Green function as in terms of this Matsubara frequency. And this can be done by evaluated by solving the Dyson equation for electrons. In this expression, G naught minus 1, this is the non-interacting Green's function. This is our electron self-energy, and this is our interacting Green's function. And now it becomes a bit another formalism. What we do, we will do two steps. First, we are writing the non-interacting Green's function, and this only has basically a diagonal form. You can see these are Pauli matrices. And then we can also express the pairing self-energy in terms of a linear combination of Pauli matrices as a function of 3 scalar variables. And this is the name of these variables has kind of a historical reason, but for example, if we just ignore this term in the beginning, we can see that this term is diagonal, this is also diagonal, and this comes from the normal state. And now this Z, this mass renormalization, is nothing, it can be shown, if you do a bit of math, that it's related to the mass renormalization that we saw in the normal state. So this is the inverse of 1 minus derivative of the real part of the self-energy with respect to the frequency. Yeah, so, and the second term is basically the energy shift. So this is just the real part, the eigenvalue plus the real part of the self-energy. Yeah, again, what we've seen for the normal state. And this second term is the superconducting, the part that is related to the superconductivity, and this we can see that is this is off diagonal. Yeah, so formally now we just introduce this expression for the pairing self-energy, and we are replacing them in the expression for the non-interacting Green's function. So remember that our goal was to find an expression for G that we can plug back in the self-energy. So we go kind of around the problem. Yeah, we will go back and forth more or less. So if we introduce this to expression in the G minus, and you do an inversion, now this is a matrix. Yeah, remember that everything is basically a 2 by 2 matrix. So you can do a matrix inversion, and what you find in this case, is this G, where I just this denominator, since otherwise the expression would have been too long, I just wrote it separately. So now we have what we are looking for. Yeah, so we have our expression for G. So we can go back to our expression for the self-energy. We plug it in. And now what we are left with, you can see that G is still a linear combination in terms of the Pauli matrices. Here we have also Pauli matrices, so we just simply do multiplication of 3-term 2 by 2 matrices, and the first term to tau 3 times tau naught times tau 3 gives us tau naught again. So here we are going to have, for this first term, this first term is going to be tau still, here it's going to be tau naught. Here it's going to remain, here, sorry, this was tau naught. This is going to be tau 3, and this, if we do tau 3 times tau 1, tau 3, this is again minus tau 1. Yeah, so if you do this matrix multiplication, what you get is this final expression for the self energy. So, but basically what we are looking for is this superconducting gap function. So so if we just stop here, we still don't really know sigma. We just have a formal expression for sigma. So we need to still use our other expression for sigma, where we just wrote it as a linear combination. And what we can do right now, we can equate the scalar coefficients of the two expressions for sigma, and this finally leads to our anisotropic Migdal-Eliashberg equation. Yeah, so basically, what we have three equations, and you can see that they are two of them are coupled, and they are also, if you were to solve this, you will need to do it self-consistently, because the terms z, chi, and delta, they appear both on the left and on the right side. Yeah, so this is quite complicated. And in fact, if you were to solve these three equations, you also need to supplement the equation with another equation that I have not written down, but this is for the total number of electrons in order to evaluate, to find the Fermi energy. So in this expression, I think there is one term that I didn't mention, this NF. This is the density of states at the Fermi level. Yeah. But luckily, right now we can do some approximation. So we are not really going to solve these three equations. So and there are a few standard approximations that one can do. And the first approximation is that only off-diagonal contribution to the Coulomb self-energy will be retained in order to avoid double counting of the Coulomb effects. And we are also going to work in the static screening approximation. So what this means is that the Coulomb contribution to the self-energy is only given by the tau 1 component of G, which by definition is already off diagonal. So it means that in this expression, so if this was the expression for Z that I had on the previous slide, basically the Coulomb contribution in the expression for the mass renormalization function vanishes. Yeah, so this is one simplification. Second, we are only working, if you remember in the first picture when I described the BCS theory, I said that we are only interested in the electrons in the vicinity of the Fermi surface. So in other words, all quantities are going to be evaluated around the Fermi surface. So if you do a bit of math, you can show that chi, the expression for chi, vanishes when you do when you integrate it off the Fermi surface, because this is an odd function. Yeah, so you are going to have the poles, and you will see that this function is going to be equal to 0. So what this means, it means that out of 3 equations, we are now down only to 2 equations. And another assumptions that we are going to do is that the electron density of states is assumed to be constant. Again, this may not be the case, and there are not too many studies. There are no studies that shows how this really affects the final results, but it's quite an important approximation. And finally, what we, or at least the current implementation in the EPW is based on the following approximation, that the dynamically screened interaction will be embedded in this semi-empirical pseudo-potential mu star. However, you can still calculate, as I will show towards the end of the talk, in principle, we can still calculate this mu star outside EPW ab initio, but it is provided in the equation through a parameter. So to summarize, what we are left, this will be our two anisotropic gap equations, anisotropic Migdal-Eliashberg equations, and that we are left with, and this is what is implemented inside the code. So Z, as I said, this is the mass renormalization function, and D and K is the superconducting gap, the same as in the BCS model. And again, we can see that the two equations are coupled, and and if you want to solve and to get the superconducting gap or to solve them, the key parameter that we have right now, or the key quantity that enters right now, is this anisotropic electron-phonon coupling strength that is basically is estimated based on the electron-phonon matrix elements. And you can formally also write this lambda, anisotropic lambda, in terms of an anisotropic Eliashberg spectral function. This is just to make a bit the connection with what you saw when you use the McMillan expression when you estimated lambda from from Eliashberg spectral function. Yeah. So to effectively get the superconducting gap, you will need to solve these equations at different temperatures. So you don't solve it just once. You will need to solve it for different T. Yeah. So this can be quite time-consuming since they will need to be solved every time for every temperature that you choose. You will need to solve these two equations self-consistently. Second, now you notice that we have this anisotropy, and this is the key point. So the equation will have to be solved on dense electron meshes, but at the same time, you also will need to do on dense Q meshes to properly describe anisotropic effects. Third, you also have this sum over the Matsubara frequency. And in principle, you should go to infinity, but in practice, we can do that. So we'll need to to truncate this somewhere. And typically, we set this frequency up to the point where, let's say, omega j prime is about, this is a convergence criteria that you'll need to check, but it's about 4 to 10 times the largest phonon frequency in your system. And I think I have one more point, is that then you also need to pay attention that this Z and delta are only meaningful for states near the Fermi surface. Yeah? So if you are to calculate this for, in fact, you can calculate them for energy states far away, but you can see that you have a delta function here. Yeah? So once you go away from the Fermi surface, the delta function is 0. So you can take advantage of this and only use a Fermi window when you evaluate this equation around near the Fermi surface. And I will give in the technical lecture, I will give a bit more details about how this is done in practice. So to simplify this, yes, yeah, sorry. So this is the form, the final expression for the anisotropic case. But in principle, you can also right now perform a second average on the Fermi surface, and you can get what is called the isotropic Migdal-Eliashberg equation. Yeah. So these are the same, but now you see that there is no dependence on the K or Q. And this is directly connected with the expression that McMillan expression, because right now this lambda is basically your electron-phonon coupling straight. So in the McMillan expression, you just have this mu j equals 0, and now you should be able to recognize the electron-phonon coupling straight. And the same here, this is just the isotropic Eliashberg spectral function. Yeah. So as I said in the beginning, the McMillan TC, and then later refined by Elendine, was found as solution or basically fitting through data obtained by solving the isotropic equation for some specific materials. Yeah, so it's just an empirical fit through data obtained by solving these equations. So I think I'm almost approaching the end with this part of the talk about the theory. Just to say a few things about the Coulomb interaction. So as I showed in this expression, I said that if you look even here, we have replaced the Coulomb interaction by this parameter, mu star. But in principle, this can be calculated ab initio because the screen Coulomb interaction can be calculated within the random phase approximation. So if we do that, once we have this matrix element, we can estimate, we can do a double average over the Fermi surface, and we can calculate mu, and then the mu star can be defined in the Morel-Anderson model, and it has this expression. Yeah, so here omega L, this is a characteristic electronic plasmon frequency. So this is of the order on electron volts, and this is again a characteristic phonon frequency. This is the order of milli-electron volts. Yeah, and we have done a couple of studies in which we have estimated this value using this approach, and then we have used basically an ab initio estimated, a first principle estimated semi-empirical Coulomb pseudo-potential that we then plugged in the Migdal-Eliashberg equations. So as a summary for the theory, we can say that Migdal-Eliashberg theory has predictive power, so it's material dependent. Yeah, I should have put an accent, but I forgot that it does. In fact, I mentioned at the beginning to the Migdal approximation. It accounts for the retardation of the electron-phonon interaction. If you solve the equation in the anisotropic form, you can use it for anisotropic superconductors, and in other words, for multiband superconductors. Generally, it just approximates the Coulomb interaction as mu star. In principle, the theory can be worked out to have this V calculated inside the Migdal-Eliashberg equation, but is not currently done. And it will require, when you want to solve it in the anisotropic case, it will require dense K and Q meshes, yeah, in order to reach convergence. I will also just briefly describe another method that can be used to calculate, to solve the superconducting gap from first principle. And this is called the density functional theory of superconductivity, and it has been developed in Hardis-Gross group. So the central part, I would say, of the SCF DFT is a superconducting gap equation. Yeah? And this formally, if you go back at the beginning of my talk, this looks like very close to the BCS gap equation. Yeah? So you can see that here we have just an extra term that did not appear in the BCS gap, but this delta is again the superconducting gap function. Z is something similar to this mass renormalization function that we have in the Migdal-Eliashberg theory, and it accounts for electron-phonon interaction, while this kernel K accounts for both electron-phonon and electron-electron interaction. Yeah, so this can be solved also self-consistently, but you can see that in this case, you only have one equation that needs to be solved, so not two equations, and as in the Migdal-Eliashberg formalism. So the method is, again, is an ab initio method, so it has predictive power, it's material independent. The way that it accounts for the retardation effect is basically through exchange correlation functionals. Since again we have anisotropy, if you solve it in an anisotropic form, it works for multi-band superconductors. The nice thing about this method is that it treats it really treats everything, both the electron-phonon interaction and the electron-electron interaction on equal footing. Yeah, so it has no parametrization as I show for the implementation of the anisotropic equation in EPW. However, it requires development of new functional to describe the electron-phonon interaction. So if you take current functional, I guess, and if you use them, I suppose that they are not working. They won't work. And again, it will require dense K and Q meshes. Yeah. So I think I will, shall I stop at this point? And then, so I can take a break at this point, and then we will see a few examples for calculation in the second part, and then we will go with the more practical implementation of these equations in the code. So questions?